Those, those international food festival yesterday. It was good. You're satisfied. Yeah. Was a lot of work for you. Like I had help from here. It's fine. From Tuesday night we had to cook. Tuesday also. You guys are involved in cooking? Yes. And you have to do all the homework also? I'll check for food marks. Did you guys try the food? I tried.
Please?
No, I was telling you, did you guys try the food yesterday?
Oh, yeah.
No. Okay.
No,
No?
no, I was teaching at the time.
Yeah, same thing, yeah, but I got it. I think one of us had some extra tickets and got to eat. Ah. Nice, yeah.
Good. I like food.
But in general, any food, right?
As long as it tastes good, it's good.
Yeah. Okay. And Pravina said she's not feeling well. So what's the gyro?
It's, I looked it up on,
Do you see the picture?
Alan Ford's picture on the website there, on I use.
Did you guys see the picture? Picture of the gyro? All of you saw it?
Yeah,
Yeah.
yeah, we see all.
You see it now? Yeah, I do it. That time I mean. It should not, it's from Howardell. Yeah. Yeah. He was a wonderful guy. Yeah, he used to be around in the department and he'll have so many things to tell. Yeah. Great guy. Who is Alan Schwan?
Sorry.
Who is Alan Schwan?
Alan Shrine, who is forward guy.
Yeah. Be the exam. What's the middle name of Alan Schwan? What's the middle name of Alan Schwan?
I don't know his middle name. No, his first and last. Yeah, the website you could also, next website with, I guess it's website there where you could, I guess they can make gyroid out of a sheet of metal.
Right, look at that.
And then they do with the little touch, and it's like little holes in there.
Who's Alan Schwan? The joke.
Okay.
Who is Alan Schwan?
It's the test question.
I don't know what is for the cycloid somewhere. I see that name.
Gyroid.
The yeah. Gyroid, yeah, it's a gyroid. Yeah. I see that name over there.
For which?
I think so. Let me see. I feel like I get that name. Yeah.
So the
Looks
exam,
like they also kind of mix, wine bottle openers
oh, I didn't know that. Tell me,
on the.
on his
website.
website?
Yeah, on this same website, and I was poking around through there and. There's dry voids as well as
Okay.
wine bottle openers.
And what was always open, but isn't it?
Yeah, which
Are you guys
always
aware of
open,
wine
but it
bottle?
can be used to open another bottle.
Are you guys aware of wine bottle? Wine bottle, wine bottle? Who's that? Wine bottle? Pradeep, what is a wine bottle? Monica? Yeah. Quiz number one for today. Wine bottle. No, you should all know. This is just popular stuff. Okay.
It's have a
Yeah,
made glass on.
KLEIN.
EIN.
It's on my bookshelf if you want to see it. Or ask how much, I think the question is how much water can a Klein bottle hold? Good.
Also smooth surface. Or
Yeah.
smooth surface.
Good, yeah, I think. Yeah, if your questions asked, Ryan, he seems to be. It's good to know.
Whenever I got it, it kind of gives me a little fact sheet with it.
Oh,
Looks it's a three-dimensional coin, two coin bubbles in 4 dimensions.
if you want to really get bonus point, print a Klein bottle on a 3D printer. You know what's a 3D printer,
Yeah, yeah.
right? All of us. Yeah.
I bet it's.
You said you printed on.
I worked with one of them.
Okay, good. Yeah. Just, but it's, you don't get credit for them. So, but I'll get impressed maybe.
Looks for a formal robot. A robot that will, helps put clear coats on electrical circuits. Check them.
Okay, let's proceed. And how's the course going? How was the homework? Has Tuesday's homework? Not satisfied.
The one we submitted.
Yeah, on Tuesday.
So
That's okay. Susan, Tuesday's homework that you already submitted? That was okay? Satisfied? Very satisfied? No, be fine, that's okay, yeah, but otherwise, work more, I would say. That's it's like, I always say that first time when you study derivative, it seems there are so many details, limit of a function, sequences and so on, but then eventually when you start using it, you're just using x raised to n times x raised to n minus 1, right? Some certain formulas. And so here we are using it as a user, but at the same time, we also need to know where it comes from, what's the purpose, but start getting the hang of it because I think it will be there all through, at least 3/4 of the semester. Yeah. I did notice that Nahida has her own way of doing it. It's pretty impressive. So ask her, maybe she will, or at least she has seen a pattern which seems to be working. Yeah, good. So, okay. So as a homework 3. And then we will get into the mechanics part of this. Currently, we are just doing a functional derivative or minimize the calculus of variation. There's a midterm 1. Not very far away. I think next
Not
2 weeks.
2 weeks instead of 2 weeks. Not Thursday.
Surely the one question will be on functional derivative. Another question on Same thing, ab initio. Is that language familiar in calculus? Sometimes in calculus, I don't know how whether it is common or not in calculus. You say prove that this ab initio. That means you cannot just write the result. You have to prove it as a proof. In a sense. So the same make the variation y plus delta y. Don't use the shortcuts. Don't use the long way. We started doing some couple of examples just for practicing calculus of variations. And I said, we started working on Brachistochrone, we constructed the problem, but then I didn't get you the equation side. It's supposed to be a cycloid and didn't derive the equation. So let's complete that. And then another example one can do is that of a catenary, Y St. Louis, which is the St. Louis Gateway Arch, has the shape of a catenary. We can do that, or we can do the sphere, the shortest path on a sphere. One of your homework problem, actually both are homework problems, I suppose, catenary and this, but either one depends on the time how much you get after Brachistochrone. I'll pick one of them and do that. Again, anything specific you guys want me to do associated with homework?
Yeah, the
Yes.
first question, the farmers, using farmers law,
Mhm.
catenary.
Oh, how to do it, you said? The first one is just whatever we have already done. I think in the class, when I constructed the formats, when you had a stratified medium, that's pretty much what it is. I did not break it into steps because it has been done in the class. So I think, yeah, it's almost straightforward. And the second one is a specific case where I give you the refractive index. Like, remember that when you have a mirage, this is a ground, I think we discussed this. Mirage, the light goes like this, right? Is that familiar? So this is ground. And refractive index or temperature goes up, right? On a hot day, temperature increases, the ground is hot and it increases. And as the temperature increases, dense air goes towards ground, or
Yeah.
right?
Let's go to
hot-
then hot go up.
Cold, yeah, hot air goes upwards, right? That's correct. Hot air goes upwards, so that's hot. So yeah. Oh, so that is cold, right? So this is hot. That's cold. Hot air tries to. What's the density? I think, okay, same point here is that refractive index. Okay. Is the density higher for hot or?
So refractive index will decrease. Decrease, I think.
Decreases.
Collier is heavier, its density is heavier, that's why that
Goes down, right? Cold.
Work with the sound of the night.
Okay. So this is denser, I think maybe, yeah, that's correct. Yeah, okay, that helps, because in the refrigerator, cold air goes down, right? Yeah, good. Okay, so this is rarer, and denser air has a higher refractive index, right? So the main idea is that refractive index goes up. Right? That's the main idea I wanted to capture out of this. Now you can have a lot of variations based on how the density of the air is going. Let's consider the scenario that it is just x, some constant times x. That's what you do in the homework problem that we did Snell's law for a general n. The second problem does if it was alpha times x, that is linearly increasing, what is the equation? Okay, so that's all you do. But again, work on it and maybe ask me again. That might be better than me going over here. Okay. Okay. Yeah, thanks. Yeah, good that you guys have started. That is the eraser. Okay. Okay. Let's do Brachistochrone. And this discusses, think of any curve starting from x1, y1. So we have x horizontal, y vertical, and gravity is acting downwards. Uniform gravity, you can always generalize this. That's a immediate question asked. You can ask that what if g was 1 over r square? Like this whole problem is not done on the surface of Earth. If it is very far away, when do you have to take care of the variations in gravity? How far should you be going from the surface of Earth if you really have to worry about 9.8? If you want to change 9.8 to the third or second significant digit, when does it change? Any idea? What about aeroplane? Is it okay to, when you're dropping a ball in an aeroplane? Does it obey 9.8 if you calculate the time using 9.8?
Decrease when you go.
It decreases, that's correct. But my question is, if you were to, let's say I drop a ball from 1 meter high, it takes a certain amount of time to reach the ground. On an aeroplane, you drop a ball, measure the time,
Then it,
how much will it change?
and will it decrease?
It decreased for sure, but how much? Like it will surely decrease because it is going to get weaker. But if I use 9.8 meters per second square, is it going to change anything? And the answer is no, it won't change. To 2 significant digit, it doesn't change. If you keep the third significant digit, it does change. 2 significant digits, 9.8 is fine until you go about 50 kilometers or even 100 kilometers, you might be okay. How far is International Space Station? It's about 400 kilometers. So there 9.8 doesn't work. What is the acceleration due to gravity in International Space Station? It's about 8.7, 8.8. You don't have to know, but it's 10% lower, right? Significantly lower. If there is an acceleration due to gravity, why does everything not fall in International Space Station? Is the question clear? Have you seen videos of in International Space Station? They drop something, everything is floating around,
Yeah.
right? But I just now said that acceleration due to gravity is 8.7 or 8.8 meters per second square. That's
two
significant
gravity
enough to-
work together. I think two gravity, there is like a Hall space, something like that is gravity will be settled down. There is like a zero gravity. Maybe that's why.
I don't understand.
Because we have the Earth gravity in the one side, another side we have another gravity.
Which is another gravity.
I think only the sun's gravity or moon.
That means on the other side it will be more. If that was the argument,
That balance, that's why there is no gravity, that's why they cannot.
But it is always, if you drop something in International Space Station, it's always floating around.
Yeah,
It's zero gravity. If you weigh yourself, how much will you weigh in International Space Station? If you stand on a weighing scale, it'll be zero, right? But then I just now said that acceleration due to gravity is 8.7 meters per second square.
Then you're
Weight
also-
to mass
Uh,
doesn't work. Mass doesn't.
True, but I mean, yes, I'm talking about weight here, not mass. But why is, if weight is mg, right? So I think the question here is weight is mg. M is of course fixed, constant. So weight is decided by g. And I'm saying that if you stand on International Space Station on a weight scale, it will measure 0. That means g should be 0. But I also said that if you calculate, so this is the International Space Station, that's about, this is R and this is about 400 kilometers. Plug it in your formula for G. G is capital G, M, mass of Earth. times r plus height, the whole square. This is the height. That will approximately come to 8.7 or 8.8, I don't remember, meters per second square. That's not zero, right? So, but all your videos show that it is zero. So why is that?
Well, it's also falling around, the International Space Station's falling around here.
That's correct. So it is because it is falling. If you're in an elevator and the elevator is falling, snap the elevator. Is that problem? So this is your elevator, right? And let's say you're standing on a weighing scale. First of all, let's say acceleration is equal to 0 for the elevator, right? It's just standing at rest. Or it could even be going constant velocity. This is at rest. So that's mg and the normal force, right? So N is equal to mg. So that's how you measure. But now let us say this is falling under gravity. That means, so you stand on a weighing scale and you jump out of a window, or that is the equivalent of falling, correct? And when you're falling, what's your weight? Right, because there is nothing to push on you, right? So you're falling, weight scale is falling. So the idea is that International Space Station is falling. Right? It is, even though it is going in a circle, it is trying to fall. It's continuously falling. So there is no axle. So it doesn't experience acceleration. So you guys are all looking for forces to balance mg. What is balancing the mg?
Normal force. Settings.
No, there is no normal force. Normal force is what is zero.
Whenever we're on the ground.
Acceleration, right? It is not balancing, it is A, and A is exactly equal to G, so you're not able to experience it here. So it is kind of saying it's inertial. Inertia is balancing the gravity. It's not a force. Right? There is no force balancing it. There is no external. But so that was because I mentioned G there, right? So you're saying it is uniform gravity. You can always modify this problem in 1 over r squared. It will be a different problem altogether. Another analysis, the equations may not come out straightforward, but it has been attempted. We are saying that it something is rolling. It can be sliding also. If it is sliding, then you have to say it is frictionless. If it is rolling, then you have to say it is perfectly rolling. And in the sense that during perfectly rolling, friction does not do any work. The amount it takes to roll is exactly the amount it has the resistance to linear motion. And in that case, if there is no work done by friction, there is only gravity coming into picture. So there is only gravitational potential energy. So if we are going from x1, y1 to x2, y2, the conservation of energy tells you that of mv squared, let's say this is x comma y, any arbitrary point, that's the velocity at that arbitrary point, plus mgy is equal to the total energy. Total energy, let us say it starts from rest. So at this point, let's say this starts from rest. That's how you can easily change the problem. What if it was not at rest? Like if I had to ask something in the exam, I say that, okay, started from rest here, do the analysis again if it is not at rest. Right, that's a small variation you can make. So if it is at rest, this is equal to 0 plus mg y1. That's your equation. And solve for this. Mass cancels out, velocity is 2 times g times y1 minus y. This is what we did last time, and if you notice, this is the same equation you have if it was vertically falling down. Like if you were to throw a ball up, it is exactly the same equation, and that happens only in gravity, where gravitational potential energy is only dependent on the vertical distance. This is also ds by dt, how much distance it travels in time, that's a magnitude, so ds would be this, right, that's here. The s, it is not in the vertical direction at all. So ds square in general is dx square plus dy square, so you can pull dx or dy. The time it takes would be dt would be ds over 2 times g times y1 minus y. Square root of that, the total time it will take is integrate both, and you start from x1 y1 and go to x2 y2 and add up all this tiny small times, and this depends on the curve on which it goes, right? Which curve you go on, that's what it will depend on. It will of course depend on the g also, but g is a constant. And in that sense, you can say this depends on the curve y. So this is dependent on the function y. So which surface are you rolling on? It could be an inclined plane, in that case, it's a straight line. It could be a circular arc. There are various functions you can think of. And typically, if you intuitively think, you would say that if it's on a straight line, the distance is shortest. So that's one way of saying that, oh, if distance is short, then time will be short. But then if the velocity is fixed because gravity decides the velocity, you would think that if you go down here, it will be faster. So in that sense, you gain a lot of speed in the early part of the descent. And since that speed will be maintained for some time, that you would think that, oh, it might be the better way to do it. So for example, come down this way, you're really going to speed up quickly, and then go in that space, same speed you travel to the other direction. But then you're taking a longer path. So somewhere in between, shortening the distance and increasing the velocity, that is a compromise, and that's what we want to capture. Right. That's no. Okay. So that's the statement, and we want to minimize this for that particular curve, and we can now write this as ds. This will be equal to, let me write it on the other side. T of y will be equal to, if I write it as an integral in dx, this is 2 g y1 minus y. And I can write this as I have 1 plus dy by dx square. And we have done this similar expression before, so by now you must have seen this structure coming out. But notice, I can also, when I write this ds and pulling out dx, right, this is equal to dx square, 1 plus dy by dx square. This is also equal to dy times 1 plus dx by dy. I could have pulled either one, and that is perfectly fine. If I pull the other one, I will, well, let's call this T1, and let's say this is T2. Then I'm thinking of this as a function of x, instead of thinking of it as a function of, so here it is y of x, right? Here x is equal to x of y. Either one is the inverse of the other. Say this is y1 to y2 dy and g y1 minus y. This remains the same. But now you have 1 plus dx by dy. But be careful here, now it's a y dependent quantity. The variation you make here is with respect to x. Here you make the variation with respect to y. Now, you can go either way. You can start from here and work the minimization principle, or you can work from here and do the minimization principle. If I do the variation in y here, take the functional derivative of y, how many places does y show up there?
For both two.
No, here. How many places does y show up?
Two.
Two, right? So that's one place, that's a second place. What about here? Not y. Now here I'm doing an x derivative. How many places does it show up? Only one, right? That's only one place it shows. So this is slightly simpler in that sense. Okay, so if you have a choice, doing one derivative is better than two derivatives. Okay, so I'm going to do the simpler one here. It immediately leads to the point that how will it work in the other case? You should attempt. Okay, that's a harder quiz, but attempt. Okay, so functional derivative d2 x over x of y I have already used, now it is y prime. Notice now it is an x as a function of y, the opposite that we typically do, and the only place it shows up is here on inside the square root. So this is y1, y2, dy, all this you don't have to worry. And here, when I take the derivative, so that's 1 over 2 square root comes down 1 plus bx dy whole square and 2 times bx dy, and then eventually you have d by dy of delta of x of y. Hopefully by now you have seen how I'm doing. I'm doing a normal derivative. At the end, I write the argument derivative instead of a normal derivative. I write it as a functional derivative where you say variation in x at 2 points is independent. This is a delta function. Now, what is this delta function? Explicitly tell me. Y minus y prime. It's not x minus x prime. Good. Right, so it's y minus y prime. Derivative of a delta function is simply the negative of the derivative of the whole quantity. That is the 2 cancels out. And I have 1 by 2 g y1 minus y. Whole thing is what the functional derivative, and there are surface terms to that which doesn't contribute, right? Plus surface terms, I should say. Which go to 0. The delta of x1 minus, or in this case it is y, right? y1 minus y prime and so on, right? That's equal to 0. Minimization principle requires that this is equal to 0. Minimization requires that the derivative, functional derivative is 0. I set that to 0. The total derivative is equal to 0. That means that whatever is there inside should be a constant. So that's 1 over 2g y1 minus y times x dy over 1 plus. It's equal to a constant. Now, yes,
This should be in prime coordinate.
that should be
Prime
Also
should
should
be
be in prime,
y,
right?
y should be primed around.
Because we.
which should be y prime. Yes, that's correct. Yes, y prime.
Right.
But then I can make it y. right?
Nice, though.
So, yeah, let's not confuse, okay, so let me write y prime, right? Good, thank you, that's very good, but at this point I write y prime to y, right, so I can change the y prime to y, so at this point, let's switch. Okay, is that clear, did I confuse anyone?
No, no, so-
But that's it, like technically it should be y prime, so thank you for pointing that out. But from here I can go further, I think from here to here, if I don't write the zero, that y prime is necessary. But in the next stage, I think I'm allowed to do that. Okay, good, okay. So technically, again, it should be y prime. I was being sloppy, now. In the next step, it's okay. And that's equal to a constant now. This is an integration constant, but let me be a little clever. Here I will say that this is equal to 1 over, just to get rid of this 2g. 2g times, it's a distance, right? This is dimensionless, so let's say this is a. Okay, that's just to cancel away that 2g. Yeah, so this is an integration constant. Is that clear? Right, derivative of something is equal to 0 means that a quantity should be a constant, that constant is arbitrary, and it should depend on the initial conditions, and that's what is clear. 2g cancels out in this way. A goes up there, and this equation becomes, so I can square this quantity, right? So square. So this is A
If we square, then the dy cancel like this.
dy.
No, 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 when we square top and bottom both, the square root goes.
Yes,
And over there, we have dx square by dy square. And the down denominator, we have dy square plus dx square. By dy square, we can cancel that 2 dy from bottom and top and bottom, and then we can just go with the x.
that's correct. That's pretty much what I'm doing, but I'm like, just since I have one line to write. So I'm going to do that in my head and check this. Correct me if I'm wrong. This is -1. That's pretty much what you said, and this is equal to dy by dx. Now I inverted it, notice, dy by dx, I suppose. Okay. Yeah. Square. Or let me write it to the square root. Right? Am I right? I think so. Skipped a lot of. That's what should it be very clear. Is that correct? Huh? That's a differential equation, right? Remember what is our goal? Our goal is to find y. Right? So that's a differential equation. So if I solve that differential equation, I will get y. And that involves an integration. So you will say dx over this quantity. Is that
It's okay. Yeah, we can cancel the 2g in the both sides, and after our remaining is.
good? Okay. So if I solve for y as a function of x, you get that. But let's
2g. Side. We have to like it change one only one side. Second one we have dx by dy square plus dx square. From here we can take the dx square out. And over here we have this one like a. When we need the dy by dx, then that comes here.
satisfied. Good. Okay. As I said, solution for this give me y as a function of x. But a cycloid is, so let me remind ourselves of what a cycloid is now, right? And I should move the camera. You boys don't help me. Okay. So what is a cycloid? And I want a cycloid. I think the main idea of a cycloid is maybe right here first. You have a ground, take a bicycle wheel, just a wheel. Different between a bicycle and a wheel, it's the same, right? So the wheel, right? And if you were to put place a LED light on this rim of a bicycle wheel, switch off the put it in dark, and then if it rolls, you only see this point. This point is actually rolling. This is going with angular velocity omega, and this is v, right? So if it is perfectly rolling, v is equal to omega r. That's your r. And this, if you were in the dark, this will actually go like this. And it will keep repeating. But this is actually on the rim, but as it is rolling, it seems like it is going this way. So probably you have seen it sometime, someone when they're driving. But what we want to do is we want to invert this. So there's sort of a this is a cycle. That's it. So that's your cycloid in the sense that that's your wheel. And this time, so if you're rolling it, correct? So this will go this way, omega, and the center moves forward. Let me not show that, just to give myself more room. So V is equal to omega r, r is the radius. And after a moment, this will become like this, right? That's your new circle. And this piece here would have moved somewhere here now. That's the path it is going to take. And we are interested in the coordinates of that point. That point is, this is x1, y1, the original point. This point is xy. Is that clear, the diagram?
See, the one is just above the line, yeah. The second point xy is above the line.
Not above, below, right? This is the
The
line.
line, just below the line, yeah,
Yes.
not in the line. In the line, that's
Not-
x1, y1.
Correct. So this point here, as it moves, so it was originally here, it has rotated a little bit. How much has it rotated? That's an angle theta, let's say. Okay. So maybe expand this more. So that's your x comma y, like zoomed in value. This was your original point. That's radius r. That's also radius r, and that's angle theta. It started from somewhere here. That was x1, y1, which was tangent to this one here. Is that clear? So this point, which was on the base of the wheel, has actually moved somewhere here, and that's decided by how much it rotated off. The wheel rotated angle theta. That's all it is doing. And in that process, it has gone a little farther, and that is v times t. This velocity is v, right? The center is moving a certain distance. V times t is the how much distance it has traveled, and theta is equal to omega times t. In a certain amount of time, it has rotated an angle of angle theta, which is decided by the angular speed. It has moved a distance x, right? Let's say this is v theta. That's all. Let me not call it x. Okay, clear? So what is x comma y? So let's start with x. In particular, let's do x minus x1. How much horizontal distance has this point traveled? That is this point, this distance here. X1 is here, x is here, that's this distance. the total distance it has traveled is V times T. So it is Vt minus of this distance here, which is R sine theta. Clear? V is omega R, so let me write omega. Or that's just theta, right? That's sorry, V times T, so that's R times 3. Write that better. So V times T is equal to omega times R times T. Omega T is R times theta. So that's equal to, so let me write this as X minus X1 over R is equal to theta minus R sine theta. Okay. Do the same thing for Y. Let's calculate this distance, how far it is. So it is Y1 minus Y. So Y1 minus Y is equal to Y1 is, so that's this distance we are saying, so that's R minus R minus R cosine theta.
Cosine theta.
So it's minus R cosine theta. Again, to write it in this form, we say Y1 minus Y over R is equal to 1 minus cosine theta. Oh, there should be no R here, right? Sorry. So when I
Yeah,
divide it
there's
out
no
by R. With me? Remember, that's the definition of a cycloid. And I'm claiming that that has something to do with this equation. Right. So this equation is in dy by dx. And that is this angle theta, which is floating around here. Theta is also a parameter. And then, so let's try to get rid of this angle theta. And we want to work in terms of derivative. So let me take the derivative of this equation. So that's minus dy by d theta. Minus, take the derivative of this equation with respect to theta. R is a constant, so R stays, and that's equal. The derivative of cosine is minus sine, so it is sine theta. And the same thing with x here, the x by d theta is equal to derivative of theta is 1 minus derivative of sine theta is cosine theta. Good. So I have a chance to write dy by dx. Yeah, divide out the 2, so it is dy by dx is equal to minus of sine theta over 1 minus cosine theta. My claim is that this is very similar to this, but that doesn't seem to be as such. So let's process this a little bit. So let's square this first of all. So dy by dx squared is equal to sine square theta over 1 minus cosine theta squared. So it is 1 minus cosine square theta divided by 1 minus cosine theta. Doing a little processing so that I can see this form there. That's equal to 1 minus cosine theta cancels. Oh, sorry, square, right? 1 minus cosine theta cancels out of that. So it is 1 plus cosine theta over 1 minus cosine theta. Let me write this as 2 over 1 minus cosine theta minus of 1. So if I were to write this, so there's a 1 minus cosine theta, 2 minus 1 is 1, and
That minus goes minus plus.
so that's plus, right? So that's the same thing. And 1 minus cosine theta, we said is y1 minus y over r. So this is equal to 2 times r over y1 minus y minus 1, which is exactly the same as this if we identify a with 2r. That's exactly the same if you say this is a a is the diameter of the wheel instead of that. So that implies that dy by dx is equal to 2 times r over, and I should say this is a now, where a is equal to 2 times r is an equation for cycle. Like this is called this curve is called a cycle. Quiz, plot a cycloid. Okay. Plot, yeah, on computer. So generate a quiz, a computer plot, or generate a plot, professional plot, like a plot, yeah, computer plot of a cycloid. It is slightly different in the sense that normally when you're plotting, you have a function y as a function of x. Here you don't have the function y as a function of x. You have y as a function of theta, x as a function of theta. Right? What are they called? Those kind of functions in mathematics?
Say that again?
So usually a function is defined as y is a function of x, correct? So that gives me a function of x and y, so there will be a function y of x. It is also possible that you say y is a function of angle theta or some parameter theta, and x is a function of theta. So x theta, as theta goes, x and y go accordingly. And if you describe a function this way, that is a
Parametric.
parametric variables, I think parametric functions,
Yeah.
parametric parametric description of a function, I guess. Very good. Description of a function. So in that sense, since I don't give you y as a function of x, it is slightly harder to draw this using the standard techniques that you're aware of. Like if I ask you to plot sine of x, you will immediately use your software and get me sine of like, for example. The easiest one, I think, is first Desmos, no,
Desmos.
Desmos, right? So that's, but probably parametric, I don't know whether it can do it or not, so make sure you use parametric plot to do that. It's a good thing to learn, that's why I'm making it as a quiz. So do try this, how to do that. In Mathematica, it's called parametric plot. If you're using Mathematica, I'm not asking you to do parametric. It's capital. And then you do x as a function. So let's say in this case it is sine of let's say t, the sine of t, and then you would say t going from 0 to 5, let's say. Right, that's the syntax for using Mathematica. Again, you should use your favorite function to do this. Okay. So that's Brachistochrone Chrome. And we can do a similar problem. Let's do the catenary here instead of the surface of shortest path being a great circle, which is also your homework. Both are homework problems. Any questions or comments on this? Anything you can add? Okay. This is this is called a catenary. And the idea is if you have two, let's say, a wire hanging about 2 points. Right. And there is a shape it takes, right? Think of an electric line. The shapes, it looks like a circular arc sort of, but it's not circular, and we want to find the shape of that. Now, there is a possibility that I hook this up here. I take a nail and hook this up, but then there is a constraint I put in there. Then I'm saying that the length of this curve is fixed. But I don't want to do that because then it's an additional constraint. I want to release that. That's another problem, that if you have a fixed length. Now, the way I want to address it here is it can hang around here. This is a sufficient rope on this side that it can pull it from. And that is a sufficient rope here that it can pull it out from. And what decides whenever there is a system and there is a choice for the system to be in two states, what is the principle that governs which one it will select? In nature? In nature, suppose there are two systems, right? Let us say you have the ability to stand here or the ball can fall down or it can go up, right? Why doesn't the ball go up when I drop it?
It's gravity.
Yeah, another statement. So there is a force acting down, you're saying. Another way of stating it in a more general way? Or energy is lowered. Like if I were to say hot and cold, like coffee can get from hot to cold or cold to hot. It is decided by energy being minimized. So one principle that governs almost everything in nature is that energy is trying to be minimized. Every system tries to attain the lower energy. So this configuration must have lower energy as a whole. That's the governing principle. Earlier we were saying, we asked the question that which time is it minimum, but now we are saying we let it go. Which state will the system take? And it will be governed by minimum energy, right? The idea is that if it goes further down, it is going to increase its energy because then it has to pull things from the other side. Right? So for example, another possibility is that I do this. Right? That's another curve, right? So I have moved this a little up. I've pulled this down. So you have pulled more things to the up. So the idea is that they all have to, total energy has to be minimized. So somehow energy has to be minimized. And let's take this curve now. And energy in this case is purely potential energy. They're all static. When you take an electric wire that is stationary, kinetic energy is not playing a role. The only energy that is coming in is the potential energy due to gravity. Like, is it going down or up? If it go up, it is more energy. Going down is is less energy. Ideally, all of them would like to come down, but there's a constraint there, right? Since it is hanging up there, at this point, they have to be up. Right, so that's a constraint. So the total, so let's first talk about a small tiny element. So that's ds. Right, so the energy of that potential energy of that tiny element. So potential, gravitational potential energy of element ds would be equal to how much? mg times height, correct? So it is dy that is coming in. So it is, let's call this, so this is x and y. So this is x and y. It is dy that is important. So at this point, let's say the coordinates are x comma y. And this could be x1, y1, and that's x2, y2. And you would say this is mg times, how do I want to say it? Help. mgy, but that's not what I want. I want an infinitesimal tiny element. So how would I do this? So I just said dy, so right? du times y. No, that's not what I want to do. Oh, this is y. Yeah, it's not m, correct? So I have to talk about, yes, I think the total mass, so let's say the density, right? So this is uniform, so let's say there's a uniform density. So mass per unit length, let's say, is density, right? So it's uniform density. It doesn't have to be, right? It could have been heavier on one side. So think of a situation where it was heavier on one side and lighter on the other side, then it will not be a catenary. So then it might be preferential on one. And but this is uniform, so maybe the way I should write this is dm times g times y. Right, that's the small potential energy associated with that quantity, and then you say that this is rho times g times y times ds. Correct? Question?
Over here, we are taking the whole y or a small element of.
A whole y. So let us say the origin is somewhere here. Right, that's your x and that's your y. Correct? And
We are
this
taking the
is
ground,
y. Right. So we are asking the potential energy, gravitational potential of this tiny element of a wire, and that is equal to, first of all, what is its mass, since it's tiny, so we are saying it is dm. Right, earlier I was writing it as m, I was being sloppy there, or I was not careful. And then it is g, and how high it is y. And what is dm? Dm, I say, is it's uniform density. It doesn't have to be, again, if by any chance this has an x dependence, that means it is more denser on the other side and less dense on the other side, things change. But let's say it is uniform, so then it is this one. And we are saying we want to minimize this. Right, that's a idea. So u now, which is dependent on y, is equal to integral of x1, y1 to x2, y2, and it is rho times g times y and ds, right, which ds can be written as dx or dy. Like the spirit earlier, we can write this as a function of x. Like so here it is y is a function of x, or I can say x is a function of y. Then I have less number of differentiations to do, and this is equal to y1 to y2 dy times rho g times y, and I have 1 plus dx by dy the whole square. Is that a familiar integral? Okay. If you recall, if I were to think of this as a refractive index, right, that's exactly the formats here on when we were doing. So this is a same problem with for refractive index being proportional to y. So if the refractive index were going higher as a proportional to y, which is exactly the second problem in your homework. Okay, so it will turn out that the second problem in your homework also is a catenary. So the path of the light that it takes is exactly the shape that is there for the electric wire. So only if the refractive index goes linearly with respect to the height. Okay, so this helps you with the second problem also. So minimize it and delta u over delta of x y prime. This is equal to y1 to y2, and that is the did I do this correct? X of y1 dy rho g y, no variation there, and this is bring it to the denominator dx by dy square x by dy, and eventually d by dy x of y. Okay. There should be a factor of 2 and 2 here, and cancel that. That we have done this sufficient number of times. This is a delta function of y minus y prime. So that's equal to this time I'll write the y prime. You guys pointed that out last time. So that's rho g y x y dy over 1 plus. And this y prime, so set it for set it to 0. You say minimization principle. Now it is energy being minimized. Earlier time was being minimized. Now energy is being minimized. This is equal to 0. So you say that, and now I also switch y prime to y, and I have y times dx over dx over dy over 1 plus dx over dy square is equal to a constant. Let's say it is a constant a. Square this again like last time. So I can say y square over a square, and I put it on the other side, so that is minus 1 times dx by dy, the whole square is equal to 1. So I have dx by dy is equal to 1 over y square over a square minus 1 integral. Yeah, quiz. Who is the architect of the St. Louis Gateway Arc? Do you know? Frank, you're from St. Louis.
Yes,
Did you know?
I've watched the documentary.
Yeah, I also-
Can't remember his name.
I also watched it this weekend. I was there in March. So they do show this equation there. It's a simple equation, I will come to that. So, yeah, so in the document they show that, so, okay, so integral dx
Can't remember his name.
and this is y. Let's write this as a times dy over y square minus a square. That's a relatively simple integral, so that's x equal to, let's substitute. What will you substitute in this scenario? What's a good substitution in this case?
Y equals A/B.
Then it will be tan square theta minus one, right? It is one plus tan square theta is secant square theta. So tangent is. Right? That's a good substitution. So. Secant. Does it secant what? Secant square theta? Because then it is. Yeah. One plus tangent square is secant square, right?
Yes.
So secant square minus one is tangent. Probably that works. Yeah, that's probably a good set, but I'm not. Okay, let's try that. Okay, how about that? I have 5 minutes. Now I want the category. Yeah. Okay, how about quiz? Substitute. Yeah, quiz is this you guys can do. Substitute a secant theta and complete the integral. Okay. I would have liked to do that, but I think I'm short of time. Okay. So good exercise. Yeah. I think. But here I'm going to do it because I want. Let's say what do we do? T. Okay. So let's cosine hyperbolic theta because cosine hyperbolic square minus one is sine hyperbolic square. So the y is equal to a secant. Sorry, not secant. Sine hyperbolic t. Sine hyperbolic have this feature that there is no plus or minus. So it's kind of easier to remember in a sense. So this is equal to dy is a times dy is a square, and then there is sine of dt. Sine hyperbolic t dt, and this is again sine hyperbolic, right? So it is a sine hyperbolic t, that cancels out, and you have a times t, right, plus a constant. Okay. So t is x minus c, it's an integral constant, over a is equal to cosine hyperbolic inverse of y over a. Right. So y over a is equal to cosine hyperbolic x minus c over a. Cosine hyperbolic function is cosine hyperbolic, let's say theta, is e raised to theta minus e raised to plus e raised to minus theta divided by 2. If you were to, let's say t, right, by theta. Because theta has this, like, you use theta so much that it seems like it's an angle. And if you were to plot this at t equal to 0, this is exactly 1, and they look like this. They grow exponentially. And that's the shape of a catenary. Simple cosine hyperbolic function. In the documentary Ryan is talking about, they really, for a second, they show his paper and they show this cosine hyperbolic function. Okay. So who is the architect of the gateway arc, right? You're from close to St. We should know. That's all. Thank you.